Hello everyone. Today I'll talk about a recent SIGGRAPH 2025 paper called RenderFormer, Transformer-based neural rendering of triangle meshes with global illumination. My name is Aaron, and this is an individual presentation for our computer graphics course. Very roughly, this work asks the question, instead of doing global illumination with ray tracing or path tracing, can we let a transformer learn the entire rendering process directly from data, starting from a triangle mesh scene and outputting the final image? In this course, we've seen the classic pipeline: transformations and viewing, clipping, hidden surface removal, rasterization, shading, texture mapping, curves and surfaces, plus ray tracing and global illumination. Traditional GI solves the rendering equation with methods like Monte Carlo path tracing. We shoot rays, bounce them around, integrate contribution from lights, and paid a high cost in computation and noise. Neural rendering methods usually still rely on rays or volumetric representations, and often need per-scene training. RenderFormer takes a different angle. It starts from the same triangle mesh representation we use in conventional graphics, but treats rendering as a purely learned sequence-to-sequence transformation. A sequence of triangle tokens in, a sequence of pixel patch tokens out. No rasterization, and no explicit ray tracing inside the model at inference time. Let me state the problem precisely. The authors want a neural rendering pipeline that 1. Takes as input a triangle mesh scene, geometry, materials, lights, and camera. 2nd, produces an image with full global illumination, soft and hard shadows, indirect lighting, glossy reflections, even multiple specular bounces. 3, worked on new scenes without per-scene or per-object fine-tuning. And finally, 4, runs faster than a traditional path tracer like cycles at a similar perceived quality. Compared to what we learned in class, it replaces the analytical solution of the rendering equation with a data-driven approximation. And it keeps the familiar triangle mesh interface, so it still fits into normal modeling and rendering workflows. The key conceptual leap here is to view rendering as a translation problem, similar to machine translation in natural language processing. In natural language processing, a transformer encodes a sequence of tokens in one language and decodes it into another language. Here, instead, the source sequence is the 3D scene. Each token represents a triangle plus its material properties, and the target sequence is the image. Each token corresponds to an 8x8 patch of pixels, represented by a bundle of 64 camera rays. The transformer learns how information flows from triangles to pixels through attention, instead of through explicit rays and bounces. So, conceptually, we are translating from triangle language to image language. To make this efficient and interpretable, the pipeline is split into 2 transformers. First, a view-independent stage that operates only on triangle tokens. It learns triangle-to-triangle light transport, roughly how triangles exchange light with each other, independent of the camera. The second stage is a view-independent stage that combines the transformed triangle tokens with camera ray bundle tokens and predicts the outgoing radiance for each ray bundle, in essence, the pixel colors. You can think of the first stage as a kind of neural radiosity in triangle space, and the second stage as a neural camera that reads out what the camera sees from this illuminated scene. Now, let's look into the view-independent stage. The input, 1 token per triangle plus a small number of register tokens used as a global scratch space. Each triangle token encodes per vertex normals with nerve-style positional encoding and material parameters from a GGX microfacet VRDF. Here, VRDF, bidirectional reflectance distribution function, is the function that describes how light is reflected at an opaque surface. Given an incoming direction and an outgoing direction, it tells you how much radiance is reflected in that direction. GGX is a particular microfacet normal distribution used in physically based rendering. It models how tiny, mirror-like microfacets are oriented on a rough surface, giving more realistic tail behavior than older distributions like Beckman, especially for grazing angles. A big issue here is position. In language models, the token index gives you a one-dimensional order, 1D. Here, triangles live in 3D, and swapping their order in the array should change nothing. The authors solved this with ROPE, rotary positional embedding, adapted to 3D. ROPE is a positional encoding method for transformers where positions are encoded as rotations applied to query and key vectors, so relative positions are naturally captured. In this paper, they derive a 3D version. They take the triangle's 3D vertex positions, map them through multiple frequencies, and use them to rotate part of the token embedding. This encodes 3D relationships while remaining invariant to poor translations of the whole scene. So, what does the view-independent stage learn? The transformer in this stage has 12 layers of self-attention over all triangle and register tokens. After training, the authors freeze this stage and train a tiny multilayer perceptron (MLP) to decode each triangle token into a 32 by 32 texture, representing outgoing radiance. The visualizations show smooth, diffuse shading across triangles, and shadows and interreflections at a detail level finer than individual triangles. So, by the time the view-independent stage finishes, each triangle token effectively carries a compact representation of how that triangle glows, already including a large part of global illumination. Now, let's look into the second stage, the view-dependent transformer. The second stage answers, given this illuminated scene, what does a particular camera see? For efficiency, the image is broken into 8 by 8 pixel patches. For each patch, they create a ray bundle token by stacking the directions of 64 camera rays, one per pixel center, and all rays start at the camera origin in camera space. The view-dependent transformer runs in camera coordinates, uses cross-attention where ray bundle tokens attend to triangle tokens, and register tokens to decide which triangles contribute to those rays, then uses self-attention between ray bundles to share information between neighboring patches. Finally, a dense vision transformer head converts these features into log-encoded HDR RGB values for each ray, which are then decoded to produce the final image. To understand what the model is actually doing, the authors visualize attention weights from rays to triangles. For a given ray bundle, the highest attention typically falls on the directly visible triangle. Significant attention is also placed on triangles located along the reflection direction, especially for glossy or mirror-like materials. When roughness grows, the attention blob spreads out, just like a real glossy lobe becomes blurrier. This suggests that, instead of tracing explicit paths, the network is learning a kind of soft, parallel path gathering via attention. So, how do you train something like this? They synthesize millions of training examples using meshes from Objaverse. Objaverse is a very large open dataset of hundreds of thousands of diverse 3D objects collected from the internet, designed to support 3D vision and generation research. These objects are placed into simple room templates with walls and a floor. Scenes contain 1 to 3 objects, up to 4,096 triangles after pre-meshing, with GGX microfacet VRDF materials, either per object or per triangle. 1 to 8 wide area lights outside the scene, and the camera always outside the scene, with an FOV between 30 degrees and 60 degrees. Reference images are rendered with Blender cycles at 4096 samples per pixel, using adaptive sampling and denoising. The network is trained end-to-end with an L1 loss on log-encoded HDR values, plus an LPIPS, learned perceptual image patch similarity perceptual loss. LPIPS is a learned metric that compares images in a deep feature space. It correlates better with human perception than simple pixel-wise losses like L2 or PSNR, and is widely used as a perceptual loss in image generation. Here are some example results from the paper and the project page. RenderFormer reproduces classic cornel box style scenes with soft shadows, colored indirect light, specular highlights, glossy reflections, and multiple reflections from several light sources. Quantitatively compared to cycles with 4096 samples per pixel at a 512 square resolution, RenderFormer generates an image in around 0.06 to 0.10 seconds on an A100 GPU. Cycles takes several seconds, even with adaptive sampling and denoising. The different images show some errors, but perceptually the outputs are close to ground truth, and the model is competitive with a fairly clean path trace reference in equal time comparisons. A crucial question is, what happens when we go beyond the training conditions? The authors test several axes. First, more triangles than 4096. The model loses some fine details and thin shadows, but overall global illumination structure remains correct. It fails gracefully, you could say, rather than breaking completely. Second, larger or fewer triangles. If individual triangles become huge, shadows and shading blur falter, because one token must represent more complex variation across the face. Then, third, more than 8 lights. Shadows and highlights become incomplete, but you can partially fix this by rendering one light at a time and adding the images, using the linearity of light transport. Finally, fourth, different cameras and resolutions. It's robust to wider FOV and higher resolutions, though errors tend to concentrate around depth edges at very high resolutions. Now for some limitations and my own critique. First, the model is still restricted by the training distribution. So, cameras might stay outside the scene because it struggles when you move the camera inside the geometry. Lights are wide area lights placed outside, because colored or internal lights need workarounds like channel-wise rendering and compositing. Finally, materials are GTX microfacet VRDFs without complex textures in the main setup, although they show some preliminary texture experiments that are still somewhat blurry. Now, second, because transform attention is quadratic in the number of tokens, scenes with very high triangle counts are difficult, but this is a classic transformer scaling issue, so it's not unique to these graphics. Third, from a graphics perspective, there is no explicit physical model of bounces at inference time. We lose some of the nice guarantees and controllability of the rendering equation. The network approximates it, but its behavior on ray corner cases is harder to reason about and debug. But I guess this can be a nice compromise. Here are some examples. In my opinion, the main contribution right now is conceptual. It shows that we can take a traditional triangle mesh scene with the same kind of inputs used for rasterization and ray tracing and feed it to a pure transformer model that outputs a global illumination image without any per-scene training. It bridges ideas like radiosity and ray tracing, but re-implements them in a fully learned attention-based form. It also aligns with the current hardware trend. GPUs are dedicating more and more resources to tensor cores and transformer workloads, so a transformer-based renderer could match future hardware better than classic pipelines. Even with these limitations, this suggests a path towards a graphics foundation model that could support both forward and inverse rendering tasks. For future work and extensions, I see several interesting directions. First, richer materials and textures. Extending the token embedding to handle high-resolution textures, transparency, and subsurface scattering in a stable way could be interesting. The paper shows an early texture experiment, but is still relatively blurry and limited. Second, better scalability. Combining transformers with ideas like LODs, level of details, or using sparse attention could support much larger scenes. Third, inverse rendering. Since the pipeline is differentiable end-to-end, it could be used to estimate materials or lighting from images, not just render them. And fourth, hybrid integration with traditional pipelines. For games or interactive applications, one could imagine systems where rasterization handles primary visibility and RenderFormer handles indirect lighting or reflections as a learned component or denoiser. These directions would bring the method closer to real-world production use. To summarize, I think this paper is a nice example of how the classical topics we already learned, like rasterization, global illumination, radiosity, ray tracing, and others, can be reimagined within modern deep learning architectures. Thank you for your time and your attention.